at 50-meter deep seabed is around 250 cm cube. So if the atmospheric pressure is 10 meter of water, so find the volume of the air bubble when it reaches the surface of the sea. So by using this, we use P1, V1 because you want to find volume, and he only provide you with volume and what you call the deep 50 water, okay, 50-meter water. So by using the Boyle's law, P1, V1 equals to P2, V2. So 60 meter times 250 cm cube equals to 10 meter times V2. So V2 should be around 1,500 cm cube. Okay, pressure doesn't necessarily must be in Pascal, or it can be in how many meter mercury or how many meter water. Okay, and sometimes in PSI as well. PSI means that 1 unit PSI means that under 1 unit of atmospheric pressure. 2 unit means 2 times atmospheric pressure, something like that. All right, now the diagram below shows a glass tube contains some trapped air inside it. So at 17 degrees Celsius, the vertical column of trapped air is 29 cm. So it gives you temperature and what I call that, the vertical column. So what's the vertical column of trapped air of 57 degrees? So we can use V over T. Okay, Charles' law. Okay, because it gives you V, gives you the what I call it gives you V. The V is in terms of the what I call that, the vertical column, the cm. Okay, so we break this V into the area, because the area of the tube always the same, the cross-sectional area. So the only difference is only this one, correct? So we just use AL1 over by T1 equals to AL2 over by T2. A is the cross-sectional area. So then A and A can be, both can be, we call the simplify. So 29 over 17 plus 273. Okay, remember it's in Kelvin. Is equals to L2 over by 57 plus 273. Move this here, you will get L2 is 33 cm. You do it correctly? Good. All right, now number 3. A mixture of air and petrol vapor is injected into the cylinder of a car engine. When the volume of the cylinder is 100 cm cube, V is provided. Pressure is 1 atm. Okay, or sorry, not PSI. ATM is the atmospheric pressure, sorry. And the valve is closed and the mixture is compressed to 20 cm cube. So the V2 is 20 cm cube. So we have P, we have V. So we use Boyle's law. P1 V1 equals to P2 V2. So 1 atm times 100 equals to P2 times 20. So you get 5 atm. Now, a gas of volume 20 meter cube at 37 degrees Celsius is heated until the temperature becomes 87 degrees Celsius at a constant pressure. So what's the increase in volume? Means that volume and temperature. So we use V over T. So which is Charles' law. So V1 over T1 equals to V2 over T2. So this is the first one is 20 over by 37 plus 273. Changing to Kelvin. This one change to Kelvin. Then V2 over by 87 plus 273. Then move this one here. So you get V2 is 23.23 meter cube. So we want to know the increase, correct? So we need to use the find the V2 minus V1. So you get 3. The increase in volume is 3.32. You didn't do the last one, correct? Done, huh? All right, now number 5. The air pressure in a container at 33 degrees Celsius is 1.4 times 10 power of power of 5 Newton per meter cube, meter square. So the container then heated until the temperature is 55. So we have temperature and air pressure. Okay, so we use P over T lah. So what is the final air pressure? Okay, so P1 over T1 equals to P2 over T2. So this one we substitute all inside and then move this here. So you get P2 is 1.5 times 10 to the power of 5 Newton per meter square. Oh, correct, huh? Okay, very good. Now let's I would like you to do Oh yeah. Oh, yeah. Okay. Try this one. Let's see clearly. Hannah? All right, try this one first. Meanwhile, give me a second. Done. Okay. All right. So let's see the answer. So diagram 1.1 and 1.2 shows that the fixed mass of trapped gas X in two identical flasks is heated with different quantity of heat. Okay. So this is the one. So state the physical quantity and its SI unit measured by the Bourdon gauge. Bourdon gauge is to get the air pressure in terms of Pascal, or we call Newton per meter square. Okay, so it's air pressure, Pascal or Newton per meter square. All right, then you see this one lower, this one larger. So both stoves are turned off after 8 minutes. Based on this, he wants you to compare the reading of both Bourdon gauge. Somehow 1.2 is higher than, you see here, 1.2 is higher than the 1.1. Now, compare the reading of thermometer. For sure, this one is higher than this one. So 1.2 is higher than 1.1. So from here, we know that when the temperature increase, your pressure of the gas also increase. Okay. Now, based on the kinetic theory, explain the reason. So when the gas molecule in the flask, it receives heat, velocity increase. So when the velocity increase, the kinetic energy of the gas molecule increase. So when the kinetic energy of the gas molecule increase, the frequency of collision between the molecule and the wall increase. So gas pressure increase. Okay? You miss out several. Okay? Yes, but this one only one cannot. Normally, we will come up with when energy increase, velocity increase, kinetic energy increase, then your frequency of collision. This is the important one you must write down. This one, then that's why your pressure increase. Now let me know. Huh? Then we got another, I think one more question, is it? Haven't discussed. None, All right, now let's see the final one. So name the law that involved when the volume of gas is constant. When volume of gas constant means that uh, P over T lah. Okay, P over T is pressure law. Okay. All right. Now with this we end the chapter 4. So we should enter chapter 5. Okay. Please take care of. Please take note of this one. This one is pretty important. Okay, so now what is the definition of wave? So it's a disturbance that transmit the energy between 2 points through the particle vibration, and at the same and during that time there's no transferring of matter. Means that you see the energy was transferred, but the particle does not move, remain at the same spot during the time. Okay, and so it's like this. So you see A, the movement is going down, B will go up, then C will go will up as well, the energy contained. Okay, because from A to B, B increase. Now B to C, so C also increase. So this is why you see the particle will like vibrate like this. This one even bigger, this one even more bigger. So somehow normally is the wave is looks like this. Why it suddenly become higher and higher? Because the energy transfer like this to it. So the energy contained here is higher, even more higher. So that's why it become like this. So you see when I jot down the graph, it will be like this. See? So you might going up, down, up, down. Okay?
But the particle doesn't move up.
It moves, vibrate only, up, down, but the position doesn't move. He still stay inside. Although it looks like that if we we enlarge very big, yes, it's like vibrate, but actually it doesn't move. It stay at the means that if you cut out the peak and lower, and then you average them, they are still at the original place.
But it's vibrate only.
Vibrate only at the current position. Vibrate only. Okay. All right. Jot this down. Done, huh? All right, so let's see the activity. This is to study the wave transfer energy without transferring the matter. So for example, the springs, the slinky spring. You know what slinky spring, the toy, okay? And then, and when we how to say, we bind the ribbon on it. So when we swing the spring, will the ribbon move front and forth? Won't, right? The only off up down, correct? So now, so why like this? Okay, you see, and the change form of wave, we call this as a propagation. All right. So uh, now when the spring is moved up and down, the wave are produced when the medium vibrate at fixed position. So the pupils at NB will experience energy which produced from the wave. And the ribbon that represent matter only moves up and down when the wave on the spring are produced. And the propagation of waves transfer the energy from one place to another without transferring the matter. Only energy was transferred. So if you swing strongly, the other side will feel the strong wave, but the ribbon won't go front. Okay, so it means that it will only keep at that position, only fixed position, and then the energy are transferred from one end to another. And this transfer of energy we call propagation with direction. Okay, can I? All right, you can this one, draw this one, and then jot this down. Done, huh? All right, now let's see the next one. So let's see the two types of waves. We have state progressive and stationary wave. So what's progressive? Progressive waves are the waves which the wave profile will propagate with time, where we have transverse wave and longitudinal wave. One is horizontal, one is vertical. Okay. Now, okay, you jot this on first. Okay, these progressive wave are the wave with displacement. Means that there is a propagation going front. If the what you call it, the we call the stationary wave, they does not have propagation. We will go through one on one. Although feels like very don't understand, right? Later on we will go through it. Don't worry. Okay. All right. Now let's see the next one. Okay, stationary wave. So stationary wave are those wave that the wave profile does not propagate with time. Normally, the musical instrument, okay, the wave from the musical instrument normally doesn't is the those stationary wave. Then there are two types of them. We have mechanical wave, like water wave and sound wave. Water wave is like when you put a bowl of water, you drop on top of it, so it will come out like this going out, right? And that is the water wave. Okay. And the electromagnetic wave, like light wave and radio wave, they are also the stationary wave as well. Okay. All right, jot this down first for this one. Okay. Right, now let's see the example of system that produce the stationary wave, or we call sometimes standing wave. You see, when a continuous wave is sent along a string to a fixed position on the other end, so it means that this one is fixed. So both incident and reflected wave, incident is going front. Okay, reflected wave is when it hit the fixed position, the wave that generate back, okay, will be formed. So in the string, so each wave will traveling in opposite direction. So the resultant waveform is called say stationary or standing wave. Why? Because it looks like standing still. Why? You see, when you move like this and you move back here, so when you combine, it looks like okay. So the wave as a whole is not progressive because it doesn't move. The energy inside the wave does not move front because it move front and back. So no propagation happen. No propagation happen means that it's standing still. So we call this as a stationary wave. Like your magnet, the waveform, the magnetic wave is fixed, correct? It won't move, correct? So that's why is what I call the if I'm is stationary as well. Okay. Okay, jot this down. Especially this one, All right. Now let's see the next one. So you see, the standing wave can also sometimes set up in pipe. So both the incident wave in and out are present in the pipe. But you see when it goes in, pop, this is fixed. So there will be another one go out. So the resultant waveform, okay, is called the stationary or standing wave because it seems to be standing still. And the wave as a whole is not progressing because it's not going front or back. Okay, no propagation. So the musical instrument depends on the standing wave along the air column inside them, especially those that need the air inside, like saxophone. I don't know the way you call it. We have saxophone like wait, forget the name for that one. Flute, yes. Okay. Flute, all these are normally stationary wave. Okay. So the diagram shows an example of standing wave in a closed pipe region. Okay. This one is only have one closed end. Okay. Now, don't worry. Doesn't need to copy this one because we already go through just now the one on top. This one looks almost similar. So now let's see the difference between the what you call. Now let's see the comparison between the transverse and longitudinal wave. Okay, so now we start with this one first. So the transverse wave are the wave where the particle of the medium in the direction is perpendicular to the direction of the propagation. You see, this is the propagation. So if I add here the propagation, this is the point, so it's 90 degrees. Because it's moving up and down, correct? It's moving up and down. This one is moving like this, so it's 90 degrees perpendicular. While for the longitudinal wave is the medium is vibrate in the direction that parallel to the direction of the propagation of wave. You know what I'm trying to say? It's like going in, going out, going in, going out like that. It's like one part will be squeezing, one part will be expanding. So that one is called the longitudinal wave. Okay, it's like I don't know the name. It's something like a piano. There's a piano key side, and then you need to like push in and out the musical instrument. That one looks like that. Okay, can all right. Jot this two first before we go through the drawing all this. None, huh? All right, now let's see the how it looks like. Like for this one, you see the for the transverse wave is like normal sinusoidal one. Okay, where you have a this this part is called trough, where it's under lower peak. The upper peak is called crest. Okay, and this is the direction of the wave propagation. So in short, from the peak to peak is the wavelength, or from from crest to crest, or from trough to trough are the wavelength, and this is the amplitude. Okay, and you see both sides, like it's on the same phase. You see, all dropping down. So we call this is the point in phase because they are on the same phase. Okay. Now for this one, the direction of propagation is going here. Why? Because you see, this vibration is going up and down. This one is going left and right. Okay. So the compression is C. Okay. This one is called rarefaction. Okay, not extension. We call rarefaction. This one is compression. And the direction of the vibration will be like this, left and right, and from the like this. Okay, we from the change. Okay, so like from here to here is the wavelength. You understand? So for this one, the example is water and light wave. For this one is sound wave. Yeah, this is easy. If you want to know how, like sound wave, when you shout going far away, you will like high low high low high low, right? Because compressed high, rarefaction low. Now for the light, normally will stay sustained. Like the water, when you drop, it will going out like this, right? It's sustained and continuous. Light also, when you off all the lights and then you switch on your torchlight, so you will see a line of light and it's consistent. Normally, that one is transverse. Okay, can you understand? All right, so jot this down. So high chances I will stop here. All right, now, okay. I guess I'll stop here lah. That's the case, huh? Okay. Just 2 more minutes. I don't think I can finish all of this. So, okay, I think I'll stop here for today lah. So we should meet each other on tomorrow evening, right? For the due time, huh? Okay. So any questions before I let you dismiss? Not yet, huh? So far, not yet. Okay. So, okay. So I think I'll stop here for today.